So this is going to be a shorter class than usual because I need to go to the class to the airport and flying out. So we'll stop around 5 minutes. Alright, so last time we looked at k-means. Today we're looking at an algorithm called expectation maximization. So often shows up as EM. We're going to today look at it in the context of fitting Gaussian mixed models. Really, EM is at the bedrock of, so if you want to understand latent variable models or unsupervised learning intents, you're the first tool that comes out of the closet is EM, expectation. And sometimes you'll see it as a softer version of k-means. So we looked at k-means already. EM is just going to look essentially like k-means, except it's going to feel like instead of doing hard assignment, we're keeping track of probability. So it's going to look at soft. And these sort of ideas of EM extend to a bunch of other types of problems. So I don't think we'll get to the general latent model learning today, but we'll definitely look at GM. Okay. That's not what it's supposed to look like. Yeah, so as I was saying, that's what it looks like. That's what it looks like. Yes, okay. So poster presentations. Next Friday, May 8th, 1:30 to 4. We're doing a poster session. This is Kelly Hall 310, that's the ICTAS building. We're running into a bit of logistical problems this year. It used to be the case that we used to do this in ECE buildings. And we were kind enough, or maybe I guess I never told anyone, but we would just stick up our posters on the wall. Now, everybody's sort of suspicious. They don't let us stick posters on the wall. So we have to arrange sort of easels and all the other assorted infrastructure needed to do a poster session. But this is next Friday. This is going to be, we'll ask you to print a poster. If you're in ECE, you already have access to a poster printer. Talk to IT, that's John Harris and Brandon King. They have a ECE department has access to a poster printer. Please print portrait, so something like 2 feet by 4 feet, something in portrait, not in landscape. We'll give you exact dimensions once we know the easel sizes. If you're not in ECE, you could just print out a bunch of slides on a printer and just stick them up on a board. Or if you're in CS, I think they have in CS. Do they have access to a poster printer? Do you have CS as a poster printer?
They do.
They do? Okay. So you have access to a poster printer as well. In the worst case, I think ECE will accommodate you if you cannot find access to a poster printer. Okay. The way to think about this is, this is for PhD students. If you've already been to conferences, this is just a poster session of a conference, right? If you're just starting out your PhD, this is a good sort of warm-up exercise. This is a standard way of presenting your results. You have a poster, you stand up there. I'll invite others in the EC department and CS departments. I don't know how many people will show up, but usually we get a few outsiders. I'll invite grad students in the department and some undergrads as well. I'll walk around with the TA asking questions, and so that will be your final presentation, if you will. Right? So it's sort of a good finishing of the project, and that's it. There's no final report or anything. This is the final delivery. Okay. Let me see. I think a couple of years ago, I had sort of gathered together. I've gathered together examples of posters to show to people that since this is a machine learning class, I figured I'd show you good positive examples and negative examples. This is a good poster. There are clear clear headers, lots of pictures, not just full of text. This is how you make sort of good posters. This is another good poster. The headers are clearly telling us what is planning to be studied. Every figure has a takeaway message next to it. And then there are some bad posters, like nobody's really things like this. This is not a poster. This is every single thing was a page in a paper. This is not acceptable. Okay, so don't do this. And don't dump an entire table. nobody could possibly read that. You won't know what to make sense of it while explaining to a person. This is not to say that you should not. This is not to say that you should not have results on your poster. There is a way to have results. It's just a better illustrated form with a takeaway message. What are we studying? What is the takeaway message from this plot? Why did you show me this plot? And none of those things are present here in a table format. Okay. All right. So yeah. All right. Okay. So poster session, format, date. Any questions about the poster session so far? Yes?
Do we have to stay the whole time?
It would be nice if you stayed the whole time, but if you have conflicts, I would understand. Please let me know if you have conflicts, and I can sort of come to you first or come to you to the second half. There are going to be people from, I'm going to send an invitation out to the CS department and the EC department. I don't know who all will show up, but it's sort of good exposure for students to have. Yes?
I'm sorry. You said to print it out, contact, you said John
Harris in EC.
So just send an email and just...
Yeah, so there's a web page on the EC department that describes the steps that you have to take. You first created like a PDF file in the right size, and then you just make sure, do not contact him on May 7th at 5:30 p.m. If he gets like 10 poster printing requests at that point of time, he will hate me. And I know for a fact that we've had this happen in the past few years. So please plan this out in advance and so have your poster ready. And I think I'll regret doing this, but here's a hack. If you're running short of time, print the poster, leave a space out in the poster, stick a piece of paper on top of it. So I know I'm going to regret this because I'm going to go and find a bunch of posters. Don't do it, but if you have to, don't mess with John, do that. Any other questions?
It's usually Brandon McKagan, actually, where you pick up the posters from.
I'm sorry?
It's usually Brandon's office that you pick up the posters from,
Yeah.
not John.
So, yeah, that's right. Brandon, those are the two people in ID, and you should get in touch with. Okay, and there's a best project prize. I'm still trying to figure out what that is. It may just involve...
Chocolate.
What?
Chocolate.
Yeah, so if I have to scale up, it'll be just a lot of chocolate. But we'll figure that out. That will be your best poster prize. Usually when I do this, I teach this class in a conjoined setting. So there's a 4,000 section, which is undergrads, and a 5,000 section, which is grad students. And so I usually pick like a winner and runner-up from both sections. So this time it's just going to be just the winner and runner-up from just one section. But in past, we've taken the winners out of the meal. I don't know if that's much of a prize. Well, you get free food and maybe some marginally relevant company, but we'll see. We might do that again. Okay. Any other questions about this? Is time okay for everyone? I know there are no classes. They're May 6th.
So what's the type of the presentation? Do we stand in front of our posters and answer questions?
Yes. So thank you. I should have mentioned that. For people who have not gone to conferences or actually done these things in the past, a very sort of good strategy to have sort of a course to find strategy. Have a 30-second pitch prepared for people who might stop by, who just want to know what did you do. If you can describe in 30 seconds what is your poster about, and then gauge interest. If they're still standing, asking questions, that's when you have a 2-minute or a 3-minute pitch prepared. If they nod along and walk off, that's when you know you've sort of saved your breath and their time as well. So it's a good idea to have different levels of preparation. I will be there asking you questions more than 30 seconds, but for others, you should sort of make sure that you have a 30-second description of your poster, and if they ask questions, then answer those questions or have a longer description. Does that make sense? And these may be students in your department or other departments, other faculty as well. Yes.
If we have results that are perhaps a little bit beyond the machine learning scope, should we include those as
Yeah,
well? to
it's
kind of give
perfectly
a-
fine. As long as, I mean, you're asking if I have 125% stretch goal done, right? I mean, you've already done the machine learning part, you want to do some extra
I
things.
just didn't know if it had to be like solely focused on machine learning.
It's perfectly fine. Talk about your project in a holistic manner. As long as it includes the relevant part about this class, it's perfectly fine. Any other questions? Okay, good luck. See you for the poster thing next Friday. And look out for an email, I'll confirm. This is getting to be far more inconvenient than I thought, but I'm on an easel hunt now. Trying to get poster boards so that we can stick this up. Anyway, okay, so here's what we were talking about last time. We were talking about clustering, we looked at k-means, and then we talked about density estimation with Gaussian mixture models. So let's quickly recap that, and so that we can talk about how do we learn parameters in a Gaussian mixture model with EM. So k-means was pretty straightforward. We said, the goal is you're given some data, you're asked, a user specified number k that says I would like to partition this data set into k types or clusters. And we came up with this observation that if you could somehow start with an initialization, if I know where this was sort of this alternating minimization view, alternating optimization, if I know where the cluster centers are supposed to be, if I know where they're supposed to be looking at it, I can very easily assign every data point to a cluster center. That's just a minimum distance computation. I need to compute for every data point a distance to every single cluster center, so it's n by k matrix, if you will, and I just take an argmain along the rows. Okay. Once I know what data points have been assigned to each cluster, I can obviously re-estimate the cluster centers. That's just computing the means of the data points assigned to this cluster. That's pretty easy as well. And with those two in place, you can set up an alternating algorithm, right? So just keep repeating those two steps, and that is essentially k-means. And formally, we wrote down here are the parameters, right? So mu's were the cluster centers, mu1 to mu k. We had two steps. One was an assignment step, so assign compute distances, assign min, and a recenter step where mu j was the centroid of its points. And what we did was we interpreted this as coordinate descent on a particular objective function. And what the objective function was doing was there was computing distance between all pairs, so every data point, every cluster center, and this was basically extracting the distance to the assigned cluster center, and this was basically sum of every data point to its assigned cluster center. And we said, okay, we have two types of variables, A, which are the assignment variables, mu's, which are the minimization, the cluster centers, and this is a joint minimization. We made a claim that this is a good objective function. It may or may not be. It was a reasonable objective function that we constructed, and we asked for this joint minimization. This is a mixed, continuous discrete optimization problem. We said, okay, let's do coordinate descent. We will fix one set of variables, minimize the other, fix this set of variables, minimize this. And that's why each of the steps ended up being exactly what we talked about. Right? So what this led us to conclude was that each step in k-means strictly makes improvement on this objective. You can only improve, you cannot hurt yourself. The objective is bounded from below, it cannot be negative. And therefore, and there are only finitely many states of these variables. So you cannot cycle. That was the main concern. Can it ever be the case that a data point is assigned to this cluster first, then that cluster first, and then keeps cycling? And it can't cycle, essentially. Because if it does, then it's making improvements on the objective, and that's not possible. Right? Okay, so that was our view of k-means. And today what we're going to look at is essentially an algorithm like this. EM is going to be the algorithm, and we'll make connections between this objective to the log likelihood under a Gaussian mixture model. Okay. When we talked about k-means being quite useful in a number of areas, of course, people trying to do discovery often do this, but even if you're trying to do ultimate classification in computer vision, people often use k-means to create a bag of visual words, if you will. And sort of this is what, if you clustered patches and images, this is what these would look like, and they're sort of serving as your dictionary is often a word that people use. Okay. So then we finally came to Gaussian mixture models, and we made a simple observation that some clusters may have more elongated shapes than others. So one way of viewing this as k-means was looking at a particular distance. It was using Euclidean distance, and we could generalize that to harmonic distance, right? And this was this idea of making this connection to Gaussian mixture models. The idea was that you have data that is multimodal, and we should be able to express that data as coming from a distribution which can be a mixture of Gaussians. So here's the illustration that we went with. This is one Gaussian, this is another Gaussian, this is a third Gaussian. This is a density function formed out of a convex combination of mixtures of each of these densities. Right? So convex combination of each of these densities is given by this. So this is a much more complicated density function than each one of these individually, which are just a unimodal density function. Okay, let's see. And we did this. We looked at this demo where we said, okay, if I have some, similar to the example that I was constructing, if I have some elongated cluster and some cluster like another elongated cluster, let's make it hard. I don't know what's going to be. If I initialize, start, show history, blah, blah, blah. In this case, for example, it takes all of this as one cluster, this is another cluster, right? And this is all of k-means doing hard assignment. What we can also do, this is what EM, or sort of a Gaussian mixture model would do if you have a bunch of points here, we initialize the Gaussians. Right, so this algorithm, what it's doing is not only estimating, so again, this is similar to the figure that we showed last time, that each of these circles is a single density function. This is a Gaussian, so there are a mean parameter associated with it and a full covariance matrix. This is a two-dimensional feature space, so the covariance matrix is a 2x2 full matrix. These are sort of ellipses corresponding to that quadratic associated with that matrix. This is another one. And these numbers that they're writing down, so this weight of 0.62 and 0.36, they sum to 1 because these are the prior probabilities, right? So this is the probability. We'll write this down on the board, but this is the even before. So this is the probability that a point, if sampled from this data set, comes from one of these Gaussians. Right? So this Gaussian is responsible for 62% of the mass of the data set, and this Gaussian is responsible for 36%. So those are all the parameters that GMM estimates. Does that make sense? The prior probabilities, these two weights, means and the covariances. And on the top, it's sort of showing log likelihood, which is the objective function that it's maximizing to do this fit. That make sense? Okay. Let's actually write this down formally on the board so we can keep track of the input column. So we're given a data set of x1, x2, all the way till xn. Right? The model that we have chosen is sort of x is this, so we want to model this data with a probability density function. We don't want this to be a Gaussian, and what we've done is we've sort of done this we've introduced a new variable z, which is a hidden variable or a latent variable, and that's indicating that's a categorical variable coming from some parameter pi. And we talked about how pi is nothing but those weight terms in that expression, right? It's just some pi1 all the way to the pi k. It's just some distribution that actually sums to 1. It's a discrete distribution, right? And x given z equals c is some normal with mu c So to map this to the picture that we just showed you, it was two Gaussians, so pi1 and pi2, those were the 0.3, 0.6 numbers that we had written. The two means that were estimated, one mean, one covariance for each Gaussian. The goal is, so what are the parameters? These are the two parameters, and this is the third parameter. This is what we're calling our parameters theta. Right? And the goal is estimate sort of theta hat ml, perform maximum likelihood estimation. And in fact, in this, so it's going to be the standard setting where it's like argmax of theta of summation I equals 1 through n of log probability of x equals xi given theta. Right? Notice your data set only consists of x's, and nobody tells you what Gaussian or what cluster each data point comes from, and therefore all you can say is that maximize the probability of the data that I've seen. And this is also known as marginal likelihood. Right? It's because this likelihood is the same thing as I equals 1 to n log summation probability of x equals little xi comma z equals c given theta. Z is going 1 to k. So you have to marginalize out all settings of z, and that's what's problematic at this point. Does that make sense? Okay. So we know that, so this is exactly what is causing, so we have to perform this argmax over all the thetas. The fact that this summation exists inside the log is what is problematic. If someone had given us a data set where it was xi comma zi, if someone had told us, magically what Gaussian or what cluster each data point comes from, then we wouldn't need this sum. Right? We would know what the right answer here is, so this sum would vanish, and this would sort of factorize into two separate terms. Right? And in fact, yes?
Sorry, why z is from categorical distribution?
Why is z categorical? So categorical is what we want to do is we want to model the phenomena that you can be one of these k Gaussians, right? So think of this, so far what I've done this, like these two steps here. This is me defining a probabilistic model, and this is a two-step procedure because this is a full probabilistic model. You can also sample from this model, right? So this is the procedure to sample from this model. First you sample a discrete variable, and then you sample a continuous variable given the value of the discrete variable you just sampled. If you do that, you generate a data set, and what we're trying to do is fit the parameters so that this data set that you generated looks like the original data that you have. Does that make sense? You can generalize that by saying that this is categorical. I'm explicitly making an assumption that in sampling time, everything is explained by one Gaussian. Right? But you can relax that assumption, and you can have hierarchical clusterings and sort of mixed membership clusterings, but we're sticking to the simple case. Does that make sense? Yes.
So maybe I'm not clear on this, but for the categorical function, it's like a dice, right?
Yeah, it's a case-sided dice.
So in this case, your Gaussians is, you could either be from this Gaussian or this Gaussian.
That's right.
But they're mutually exclusive. It can only be from one.
In order to generate the data, yes. But given a data point, given x, we don't know which Gaussian it came from. Right? It could have come from. So in order to create this data set, what you do is you first pick a Gaussian, and then you sample from that Gaussian. Right? That's the generative view of this data set. But if I directly give you an x, here's an x that I think I've sampled from this distribution. We don't know what Gaussian it came from. Right? Those are the sort of inverse views of this. Okay. All right. So this is going to be the key problem that we're trying to solve, and somehow we're going to use the fact that if I knew what Gaussian I came from, what each data point came from, then this problem would be easy, right? And we're going to make use of that. But as we looked at last time, first what I'll show you is I'll try to argue that this objective function, this marginal likelihood function, which is a seemingly innocuous function, is actually quite ill-conditioned. Doesn't behave very well. Okay, this is what we were talking about last time. The first thing that we said was fully observed log likelihood factorizes, but marginal log likelihood doesn't factorize. And that's because there was a sum sitting inside the log, and that's what that does is it couples all the parameters of all Gaussians together. It means you can no longer nicely parallelize or solve things completely in isolation. You have to really solve the joint problem. The other thing that we talked about is this problem of identifiability. Right? We talked about how if you have one-dimensional data and you have to estimate two parameters, mu1 and mu2, this is a 2D view of the heat map or the contour map of the log likelihood, the marginal log likelihood. And what we see is that there are actually two peaks. It's because mu1 could be 10 and mu2 could be minus 10 or the other way around. Right? That's the x-axis values for this. You could swap those two. So there's an entire permutation of parameters that achieve the same argmax of the marginal log likelihood, which means that this function cannot possibly be convex or concave in this case, because it has multiple maxims, local maxims. The third thing that we talked about at the very end of last class is the fact that this marginal likelihood function has singularities. In the sense that we showed you this one-dimensional thing, and there was this one Gaussian, if you center it on exactly one point, and if you start reducing the variance of this Gaussian to 0, it assigns infinite likelihood to this one data point. And that basically means that your objective function, which is what we were trying to show you here, in terms of, this is only mu1, mu2. If you also think about the fourth dimension, which is sigma 1, sigma 2, it basically has singularities. It certainly vanishes to, or increases to positive infinity. So the problem there is that if you actually write down an algorithm that maximizes that function, at some points you'll notice that that value is increasing to infinity, and that's when you stare at your covariances, you realize it's actually collapsing. Right? So you don't want such a result. Right? This is all in one dimension, so we know what collapsing means, but in high dimensional data, right, this is one-dimensional data. If you have d-dimensional data, it's no longer, variance is not a number, it's a matrix, right? It's a covariance matrix, and what's happening is that the rank of that matrix is less, it's less than full rank. Right? And that's even harder to detect, or not immediately obvious from looking at the numbers. Does that make sense? And somebody asked this question at the end of last class, why does this not happen if I have a single Gaussian? Right? Does anybody know why that wouldn't happen? So, I guess fitting a Gaussian to data is just hard.
That's a good question. So
Yes, yeah, I know. Does anybody else know? Because we've done, like, you guys have, like, fitting a single Gaussian to data is not hard, right? There are two parameters, mean and variance, right? Let's think about one-dimensional Gaussian. How do you compute the mean? You just take the sample average, that's the mean parameter. You just take the sample variance, that's MLE. We know we can do it in closed form. So clearly there are the likelihoods are not going to positive infinity. Why does this not happen with a single Gaussian? The intuition is that if there was a single Gaussian, and if it was collapsing on any single point, e to the negative of that point is 0, sure, but for any other point, you're also assigning a 0 probability over your Gaussian, right? So log of 0 is also going to negative infinity. Right? What's special about two Gaussians is that one of them is collapsing, and any other point is being explained or being given non-zero probability by this other Gaussian. The other Gaussian is not collapsing. And so log probabilities are still fine, they're still real numbers. But if there was only one Gaussian, there's nothing else to cover the thing, if there's one Gaussian and its variance is going to 0, then it means that you pick a point that is not where it's collapsing, and you're basically assigning it 0, so log 0 or negative infinity, or not defined. Does that make sense? Okay. So, alright, so enough. So, the reason why we went over these problems is because we wanted to sort of convey this idea that this thing that we just showed you as a demo on a website should be difficult. Right? The fact that you can, this function is quite ill-conditioned. But let's make a specific connection to k-means. Let's argue that I can make certain assumptions, and maximizing this marginal log likelihood is the same thing as minimizing the objective function of k-means. Okay. So here are the assumptions that we'll make. So what I'll do is on the right side, I'll make 3 assumptions, and under those assumptions, I'll write down this objective function as the same as the objective function of k-means. So here's sort of assumption 1, that a priori all Gaussians are equally likely. Basically, pi c is 1 over k for all c. Right? If you think about it in clustering, while assigning a point to a cluster center, we don't try to reason about, is this a bigger cluster center or is this a small cluster center? Does this cluster already explain something, right? So what we're trying to do is set certain assumptions on variables here so that it essentially matches k-means, right? So here's assumption 1: all clusters are equally likely. Okay, and we're not going to estimate these parameters. We know what these parameters are. So now the parameters left are just these 2: mean and covariance. We also know that in k-means we don't estimate the covariances, so we have to make some assumption about that. Right, so here's assumption number 2, which is spherical Gaussians. Which is that the covariance matrix C is the same for all C. Right? It's identical. Every single Gaussian has the same covariance, and it's essentially sigma squared, sigma squared, sigma squared on the diagonal, and 0 to nullified. Right? It means if you think about those ellipses, they're always sort of circular lines. The contour maps of those Gaussians are always axis. So they're axis aligned, and they're always sort of circles. This is sigma squared identity. Right? And what this does is, if you think about the PDF of a Gaussian, so probability of x equals I given z equals c, this just, so let me write proportionality. So this is proportional to e to the negative x minus mu c transpose sigma c inverse. Sorry, that's too far in the corner. Most people can't see. So this is just a standard Gaussian, right? X minus mean, covariance inverse, x minus mean. If the covariance matrix is a diagonal, the inverse of this matrix is just sort of sigma c inverse is always identity divided by sigma squared. That's just the inverse of this matrix. And what that does is, it means that the PDF is just e to the negative of x minus mu c norm squared divided by 2 sigma squared. That makes sense? It's getting there. It's beginning to already look like the k-means objective function, right? Taking out the covariance matrix, 1 over something constant, there's exponent of the negative, the log probability coming, and it's going to become a negative distance, right? You can already sort of see it. There's just one extra assumption that you need to make, so it's the final assumption number 3, which is hard assignment. So hard assignment assumption is that a data point can only be assigned to a single Gaussian, which is basically to say that probability of x equals little xi, z equals c. There's only one data point, right? So this is I can set z equals 1, I can set z equals 2, and it'll still, a Gaussian mixture model will give some probability, right? You can set from the first Gaussian, it may be really far away, but it still has some probability. This is just saying there's one, pick any one, and that's the one that assigns you any probability. And so this is just proportional to, if I think of it as, a bunch of cases, it's 0 if z equals, let's say 1, 0 if z equals 2, all the way till some value z equals some c, and it becomes probability of x equals xi z equals c. Right? There's some c star, if you will, where you get a value, everywhere else you're basically 0. What this assumption does is it essentially knocks out this summation. Right? It means that there's only one Gaussian which can have any non-zero joint probability. Right? If you pick a Gaussian that's really far away from you, then it's probability 0. Okay, so the summation has been knocked out. Pi doesn't exist. There's only sort of e to the negative of x minus mu squared. You've sort of made that assumption, and under all those assumptions, you can sort of easily show that this is equal to summation of I equals 1 through n x I minus mu j squared divided by 2 sigma squared. There's a negative here plus some constants. Right? This summation of log probability is the same thing as summation of negative distances. And therefore, k-means, which is an algorithm for minimizing this, maximizes that. Does that make sense? So, just to step back, if you make the assumption of spherical Gaussians, which seems reasonable as far as k-means is concerned, right? When you assign a data point to a cluster, you don't reason about which axes am I counting distances in. Hard assignment, because k-means can only reason about assigning it to one data point, and all Gaussians are equally likely. Under those, it's actually precisely identical. It's not just an analogy. Yes?
Third assumption is because k-means doesn't have overlap.
K-means doesn't have overlaps, exactly. It is not the case that you can have two Gaussians which are sort of overlapping, therefore one point gets some probability assigned from this Gaussian and some probability assigned from this Gaussian. Exactly. Does that make sense? Okay. Let's look at this visually. So, yeah, so spherical Gaussians, one class. So k-means, if you think about it, if you think of k-means as a particular set of assumptions, then here's how you would generate data under those assumptions. Here's what that sort of Gaussian mixture model looks like. It basically means that you have a bunch of mean parameters, and these are your Gaussians, right? In 2 dimensions, these are axis-aligned spherical Gaussians. The variance in each dimension is constant. The variance is not a function of both of those parameters. There is no covariance, right? The 2 features are completely independent in this case, and this is what those 2 look like. They're all identical. And if you want to sample the data point, you pick one sort of Gaussian. These are all equal probability, and then you get a point from that. Whereas a full GMM can have arbitrary sort of variances, covariances. This one is not axis aligned, right? So this actually does have a covariance matrix. This one is nearly axis aligned, but at least it's not sort of sigma squared I is not the same as sigma squared j, the 2 dimensions. And here the Gaussians are also overlapping, in which case the data point could actually have some probability assigned to it from both Gaussians. Right? So you would pick one Gaussian and sample the data. Does that make sense? Okay. Let's see. So we looked at this demo. I think at some point I was playing around with this. Yes. Okay. So the demo actually crashes at some point. Yeah. So this is the log likelihood. Coming back to this demo, this is the. Okay, we'll stop in a second. This is the log likelihood that is being maximized. Remember, log probabilities can be negative numbers in this case. This is the prior pi 1 and pi 2 being estimated, the means and the covariances. And in fact, in this implementation, sometimes 3 works. So this is 3 Gaussians explaining the same data. What I realized was that it was pretty clear that they were not preventing the collapsing problem. So at some point, the implementation crashes. Like it just disappears because you start having these NANs in the log likelihood. Yeah, this is the case where you have a Gaussian whose covariance matrix has reduced rank nearly. It has not fully collapsed, but if it wasn't for this point, it would have a rank 1 covariance matrix. So even though it is a 2-dimensional Gaussian, it only assigns probability along a 1-dimensional affine space, and therefore you would again get one of those cases where you start cycling through the problem.
Can I ask a question?
Yes.
When it converges, what are the weights actually showing here?
When it converges, the weights are actually showing those pi, right, so it's behind the screen. We're showing the prior probability for z. So it was saying that if you wanted to sample from if you wanted to create this data set, 52% of the points would come from this Gaussian. So when you first started sampling, there's a 52% chance that you would pick this Gaussian to create a data point. Or alternatively, another way of thinking about this 52%, this Gaussian explains 52% of the data if you want to think about it. Does that make sense? There's 17 and there's 20. This is probability of z, if you will. Yes?
Is it not converging, but it seems like it's oscillating?
Is it really oscillating?
Yeah, same. I mean, at least in the previous example, it was
2,
obvious.
1, 3, 3, 7, that's okay. 4, 5, 4,
It's
1.
10 to minus.
Yeah.
Interesting. Yeah, it's definitely not monotonic, right? It's not improving, which is odd.
With the two Gaussians case, it was obvious. It was only 2 states it was oscillating.
I see. Yeah, it's not clear to me because if they really did implement EM, then you should have monotonic, and we haven't told you this, but we'll maybe not today, but we'll get to it next time. We'll show you that EM, the algorithm for picking these parameters, also essentially looks like a coordinate descent algorithm, and therefore the objective function can only go up. But I'm not sure what's being done here. Yes?
Let's say I have data that is high dimensional and I don't have any knowledge about it. Is there a mathematical way to find a good approximation of what could be the right number of categories?
No, not. I mean, so there are sort of multiple ways of going about it. So, for example, now that we've made this probabilistic connection, you can start talking about, I wrote down a particular probability model where I first sampled z, then I sampled x from z. You can add an extra variable which is k. Right? K is a number that you could first sample. How many Gaussians do I get? And maybe that could be coming from a directional distribution or a categorical distribution. Pi could be coming from a directional distribution. So you get all of that, and then you would sample x. So you could write down a model where it would learn how many Gaussians it needs to fit this data set. But in general, you would always observe this case that if your objective is log probability, you can only do better by having more Gaussians. So the problem and this is what I was talking about, the problem in unsupervised learning tends to be in defining the objective function. What is it that we care about? And usually we care about so many things in so many different domains that sometimes you care about discovery. Like you have a user who wants to look at the clusters and decide. And that's not really an objective function that we can write down, right? And therefore, whatever objective function we write down usually does better with more clusters. You can put priors and sort of push it away. In practice, what sort of things people often use in k-means or in GMM, you start with a small number of clusters and you look at the objective function as a function of clusters. So you'll probably, on x-axis if there is k, on y-axis if there is objective. So how well is my clustering objective doing, whether that's a k-means objective or GMM. In general, you will find that if we're minimizing, in general you will find with larger k you're doing better. At some point you might see a sudden drop the reason why that would happen is before this you were under partitioning, and that's at this point of time there's the right set of partitions, if you will, and after this there may not be too much improvement. So usually people look for such sudden drops. But again, what is the y-axis here and how much is sudden and what range you decide that is sort of things that you look at the data and you sort of decide. Does that make sense? Okay. Let's take a minute here.
Alright, well basically I'm just gonna miss the length of it, the part, but they'll deny. So they won't. Because it's one of those.
I don't know in that case.
Right. Can't really.
The algorithm comes out and says that you will solve it.
Well, so I can say we were
A number of communities end up rediscovering that algorithm.
so I think if I live here in 3
And at some point somebody sort
and work,
of sits down and makes the connection and makes it. It's usually quite rare that you do a whole bunch of math that leads you to something that is elementary that you could have captured. It does happen.
oh, that's right.
Which direction? But it's not really based on this. Additionally, you don't realize if the question is supposed to be asked about A given B or B given A.
We're talking like about
See, we could have like a dimensional distribution. Again, the category of the two categories are the same one, just what is one it's the probability of C. What is the probability that a data point comes from that constant? That's what K means. Not for this is GML. This is Gaussian mixture model. Like your guesstimate. Yeah. I think you're okay. Well, your so when you want to okay, let's assume. So I think you're multiplying stuff. Alright, we're going this way. Okay, so we're going to now this algorithm called EM, or expectation maximization. As I mentioned, so it was invented or discovered in really early on, and we're going to first look at it for estimating Gaussian mixture model parameters. It's again going to look like an alternating minimization algorithm. It's going to look like soft K-means. And here are the two steps that are involved in EM. The E step stands for expectation, and initially it's going to be unclear why we're calling it expectation. But later on, when we explain the general algorithm, it will be clear why it's called expectation. And then there's an M step which is called maximization. And I'll write this down on the board next, but what I want to just say is that what the E step says is for each data point xi, go ahead and tell me a soft assignment to every single Gaussian. Right? So if you compare that to k-means, this is not a hard assignment. So z given x and for a k-means is a 0-1 probability thing, right? There's only one cluster that you can assign. Here it's a soft assignment. So this could be a full vector of length k with numbers that sum to 1. Right? So it's the probability of z given x. Where did this data point come from? And once you do that, the next step is to maximize log likelihood. So basically assume that we know what this is, we know where each data point comes from, and it's a fully observed log likelihood, and therefore it's essentially sort of like fitting a single Gaussian to a data set that is provided to you. In the sense that if I tell you that this data point came from this Gaussian, all you would have to do is accumulate all the points associated with that Gaussian, estimate the means for those points, and estimate the covariances. Here it just becomes like a softer version of that. No data point is fully assigned to you, it's just you're assigned with something. And so you end up computing weighted means and weighted covariances. Does that make sense? Okay. So I think I should show a picture of this. Here's what this looks like in terms of pictures. Here's the start of the algorithm. Each circle here is a data point, and I'll explain the pie chart in each circle in a second. But these are the initial, there are 3 Gaussians. There's a blue Gaussian, the red Gaussian, and the green Gaussian. Right? These are the initial parameter values. The p equals 0.33 are the pi's. So you are also initializing. So you start off with initializing pi c at time 0, mu c at time 0, and the covariance matrix c at time 0. Right? These are all the parameters that you have. That's what this is doing. So 0.33 is about as good as any initialization, completely uniform. We don't know what the size of each Gaussian, if you will. The centers are estimated somewhere here. This one is a sort of spherical Gaussian. The red one is some shape, and that is some shape as well. What each of these pie charts are showing is that probability of z given x. Right? So that's what this algorithm was doing. The E step is estimating, tell me the probability that this, if I tell you with this x, how likely is it to come from this z? So a point out here is only explained by the green Gaussian. It is too far from the blue Gaussian and the red Gaussian, and therefore it is largely green. A point in here is right underneath these 3 overlapping Gaussians, and therefore it has a nearly uniform distribution. So this is a soft assignment, right? This is roughly like 0.3, 0.3, 0.3 in terms of this pie chart. And that's why there's a different conditional distribution at each point. Probability of z given x, probability of z given x, z given x. Does that make sense? Once you've done that, this is iteration 1, you've estimated z given x. Now that you know that this data point is assigned sort of 1/3 to this, and this data point is nearly not assigned to this, and this data point is assigned less than 1/3, and this is more than 1/3. What the blue Gaussian does is accumulates all data points that are assigned to it, computes weighted means and weighted covariances, and updates the means. Does that make sense? So here's iteration 2, because this is at iteration 2, and so this is the blue Gaussian, the new center, new covariance, the red Gaussian, and the green Gaussian, right? And you again go ahead and estimate P of z given x. Those are the pie charts at each data point, and each of the prior probabilities for each of those guys. Right? As this algorithm continues, you basically find these Gaussians fitting to each of those data points. And at convergence, it is not guaranteed that these soft assignments will become hard assignments, but as the Gaussians are fitting to them, it is likely that they will become more and more peakier. In some data sets where you actually, if I had initialized this with 4 or 5 or 6 Gaussians, it would be the case that some of those would be overlapping. At convergence, you could have some point here with probability of z given x, sort of 50-50 coming from 2 Gaussians. Does that make sense? Yes?
What was the initialization for the covariance matrix in this case?
So I don't know the numbers, but this is the start of the thing, right? So it's a 2-dimensional feature space, so it's a 2x2 matrix. So this one is spherical. It means that you can think of it as an identity matrix, right? A scalar version of an identity matrix.
Does it matter if I pick the same one for all the Gaussians?
No, it's like, usually that's a safe bet. You sort of initialize with, because a priori you may not know how to sort of do a good initialization, and so identity is usually a safe bet. What is also commonly done is, people will often force run k-means to convergence, get an idea of sets of clusters, then use those clusters to initialize sort of a covariance matrix and start with that. It's sort of a good way to very quickly sort of have an initialization. Does that make sense?
How do you update the covariance matrix by the weighted sum? I'm just curious. How do you do that?
We'll write that in a second. Yeah. Okay. Okay. Now that we have that picture down, let's do the math on the board. Okay. What is this? All right, so we already said this was the initialization. You initialize all your parameters. Step one consists of sort of fixing, so if these are all your theta parameters, at any point t, you fix your current set of parameters, theta t, and what you go ahead and estimate are these things called soft assignments. So I would say a of I comma c at time t. If you remember from last lecture, we had defined this as an association vector. If it's a binary vector, in this case, it would not be a binary vector, it would be a soft vector. So AIC is the association of point I to cluster or Gaussian C, right? And we define this as Z equals C given X equals Xi, comma, theta T. If I tell you where the current Gaussians are placed, can you tell me what is the probability that this data point comes from this cluster center, right? And the way to do this is just application of standard sort of Bayes rule. I'll write this divided by probability of X equals Xi given theta T. Right?
There is a given in the numerator.
Thank you. There's a given there. Yes. And I can introduce Z in the denominator and multiply that out. Z is equal to C prime or J. Let me say J. Z is equal to J, summed over J. And I can write that as probability of Y vector. Alright. No, actually, we'll have to write this one. So it's basically probability of X equals Xi given Z equals C, comma, theta at T divided by summation of the same thing and the probability of Z equals C. Same thing times same thing summed over T. Right? Does that make sense? And this is pretty clear what this is. If we already know what this is. Like if you're just being asked how likely is this Gaussian given these parameters, well, we just have to pick that parameter, right? If we already know what the value of that parameter is. So this thing is just pi c at time t, right? And this thing is just feed it into the normal with mu c at time t, comma sigma c at time t, right? Divided by a normalization constant. So what this means is take a point, go to Gaussian 1, ask it how likely is this point under this Gaussian, multiply by the prior, do this for every single Gaussian and normalize. Right? That will give you the posterior probability. Right? So at every iteration, the one step of getting these associations is just checking against every single Gaussian of how likely am I to see this point from that Gaussian multiplied by how likely the Gaussian was that a priori and just normalize. Right? Okay, so this is step one. Fix theta, compute these associations. The next step will be exact opposite, which will answer your question. How do I fix the associations and compute the thetas? Right? Can I erase that slide? Because I'd like to keep this slide. Okay, so remove that. So this time, we know what these associations are at time t, and we're asked to find theta of t plus 1. Right? And it's basically this. Theta is the argmax of this likelihood, only there's a difference now. This time we don't have to marginalize, because we know what these, each data point is assigned to something, so we know what that is. Right? That's the AIC that we just computed. And so what that does to this marginal likelihood, it just becomes theta t plus 1 is equal to argmax of theta summation I equals 1 to n, and you have an EI log. Sorry, there's a summation over C AIC at time t log probability of x equals xi, comma z equals c. Thank you. Given that's what we have. Okay, what does that even mean? What have I written down? What I've written down is, so imagine imagine AI was the binary vector, right? It was 1 of k encoding. So it was, let's say, 1 for a particular Gaussians and zeros for everything else. But imagine if that was the case. What is this sum doing? It's just, like this sum is just saying, go to every single Gaussian and compute the probability that you come from that Gaussian, right? And then that multiplied by, I'll just pull out that component. And if this is not a 0-1 vector, if these are probabilities, then this is just a soft version of that. I don't have to change the equation, it stays exactly the same. Right? Because someone told me where each data point came from, which Gaussian. Right? And this, the difference between this and this is crucial. It's because now the summation sits outside the log as opposed to inside it. Right? The summation sitting inside the log means that this doesn't factorize. Summation sitting outside the log means that this sort of nicely factorizes. If it was a 0-1 case, I could actually write this thing down, 1 for each Gaussian, right? I could sort of recount this as first I could count over all Gaussians. Then I could say sum over I such that AIC is equal to 1, and then the log probability of that. Right? So I could have swapped these two, and basically AIC is just sitting in here. Which means that this is a separable learning problem, 1 for each Gaussian. We know how to fit Gaussians, we've done MLE and Gaussians, right? And the answer for this, like mu hat MLE, ends up just being, for a regular Gaussian, if it was 0-1, it would just end up being, take the average of data points assigned, so AIC equals 1 divided by number of, so summation of 1 AIC. Does that make sense? So take the data points that are assigned to the cluster center C and take the average of those. This is what would happen if you had a binary assignment. If you have a soft assignment, nothing changes. It's just I end up writing AIC here, right? And sum over all I. Does that make sense? I'll write this clean out here. It ends up being AIC xi sum over all I divided by summation of AIC sum over all I. Right? AIC is some number. It's some probability. Right? We're doing this for Gaussian number 1, say. Right? So it's some number like 0.2 for data point 1, 0.5 for data point 2, 0.7 for data point 3, something like that, right? So it's a weighted average divided by sum of all the weights. And you do the same thing for the covariance matrices. So sigma C just becomes sum over AIC xi minus mu C xi minus mu C transpose. This is just the estimator of this is the sample covariance, right? Take every data point, subtract it from the mean, take the outer product with that same data point, sum it over every single data. This is just a weighted sum. And that answers your question. That makes sense. And similarly, you would define pi c, so this is mu ct plus 1, sigma c t plus 1, pi ct plus 1, which is just count. Sum all the way to ic divided by how many, what is the total mass that was assigned to this Gaussian C? What is the total weight that was assigned to this Gaussian C? Does that make sense? And that's it. So you're basically alternating between these two steps. You're computing this assignment again. Under these assignment, you're computing weighted means, averages, and priors. And this is where you can see the analogy to k-means. K-means does not estimate this, it does not estimate this, and it estimates this in a hard assignment fashion. And that's the hard assignment. So you make that softened and use the soft assignment. Does that make sense? Okay. So we'll stop here, and next time we'll connect this particular algorithm. So today I just sort of proclaimed that this is a good algorithm. Next time I'll show that this is optimizing some. All right.